Good afternoon. I was having a bit of a giggle there because it's funny how strange all these things sound when you write them out. Normally we have acronyms for all of those things and they're really short words. But when you actually have to write them out, they're really long. It's a real mouthful. So I think the key in my title is the engineer word. I'm not a physicist. I'm an engineer, so I'm concerned mainly with building the signal processing systems on these telescopes. But having said that, I do think it's necessary to take a little bit of a look at some of the basic physics, just to remind ourselves of where radio astronomy comes from. So I spent the first week in July at a meeting just outside Florence at the Arcetri Observatory, and the meeting was actually hosted in Galileo Galilei's old house. And that reminded me that astronomy itself isn't all that old, but that the radio astronomy is actually a very young science. And so I want to just briefly outline a little bit of the history of radio astronomy, very basic stuff, before I will lead into a little bit of the radio astronomy revolution, and then how that led to South Africa, and particularly to today, what we're developing at the moment, the Meerkat radio telescope, and then looking towards the future, towards the square kilometer array. So as recently as 1800, we as a civilization were not aware that there was radiation outside of the visible spectrum. And it took William Herschel a chance discovery. He was trying to measure the temperature of the different colors of light. So what he'd done is he'd set up sunlight to come through a prism, and then set up several thermometers in those different colors, and he sort of noted down the temperatures. And he noted that towards the red, things got a little warmer, and wrote down his findings. And a little while later, he came back to his experiment, and he noticed that the thermometer that was outside of the red range was actually reading hotter than anything else. And this was the first time that he realized that there must be energy that he couldn't see. And that was the discovery of infrared light. And that was only in 1800. And as I've noted here, a serendipitous discovery. So then things developed along those lines, and in 1865, James Clerk Maxwell published his dynamical theory of the electromagnetic field, which is really a huge leap ahead. And he predicted from these collection of equations that he wrote up that electromagnetic radiation should propagate at a certain speed, and he noticed that speed was exactly the already measured speed of light, and that was really too good for a coincidence. And so the realization started to set in that light is actually electromagnetic radiation. Then finally in 1889, Heinrich Hertz demonstrated the transmission and detection of radio waves. So now this was really becoming accepted in the mainstream science. And people realized that they could observe the sun, for instance, in the radio waves. And there were various attempts in the 1900s to do this. So Edison and Kennedy wrote a proposal for this. It's not clear whether they proceeded with that, but either way, no positive results came from it. Wilsing and Scheiner did some work in 1896, Lodge in 1900, Nordman in 1905. All of these are interesting things to go and read up on what they tried. The unlucky one here is Nordman, who actually did everything correctly. And when we go back and analyze his receiver system and his antenna, we realize he had enough sensitivity to detect the sun. But it happened to be that when he climbed up to this mountain where he did his observations, it was a solar minimum. So he was really unlucky. Then in about 1900, Max Planck formulated the black body radiation law, which gave us an idea of what radiation to expect from, for instance, the sun. And because of the curves in that, and you can see that over here with the different temperatures, so if something gets hot, it emits energy, but the peak in this is kind of here in the 500 nanometer range. And as you go up in wavelength, in other words, lower in frequency, that energy was less and less. And so they realized that they would need incredibly sensitive equipment to try to detect this very low energy out there. And of course, electronics wasn't as developed as it was today, so they could really only operate at very lower, at the much lower frequencies. And around about the same time, Heaviside predicted that there'd be an ionosphere surrounding us, and that would be reflecting radio waves from space. He was actually interested in that from another perspective of internally reflecting radio waves around the atmosphere in order to communicate beyond line of sight. And the combination of these things and the failed attempts probably discouraged some further attempts. So it took a long time before anyone else took this up. And in fact, it took serendipity again to detect signals from outer space. So Carl Jansky in 1931 was trying to build a communication system. And what he built was an antenna to measure all the different types of interference so that he could characterize them and get rid of them, so that he could build a better communication system. And he detected what he called a faint, steady hiss of unknown origin that was just interfering with his actual communications all the time. And he eventually looked into this, and he determined that the period of this was 23 hours and 56 minutes. So there was a peak every day, but it wasn't 24 hours. It was 23 hours and 56 minutes. So it was the sidereal day instead of the solar day. And therefore he could conclude that this, and by carefully looking at star maps, he could conclude that this radiation was coming from the Milky Way. And this was the big breakthrough. That's a picture of his antenna. Well, this is not his actual antenna. This is a replica that was built after the fact. So a very, very crude kind of system. That was a bad time to be making scientific breakthroughs. For one, it was the Depression, and closely followed by the Second World War, which might be part of the reason why no one really followed up on this very quickly. But it did inspire a man named Grothe-Reber, who did something extraordinary. He built a 9-meter dish in his backyard, and he actually confirmed Jansky's discovery in 1938. And he also created the first radio maps of the sky. These are kind of broadly the Milky Way with some peaks associated with what we now know to be radio sources in the sky. So he first tried this at 3,300 megahertz, and then later at 900 megahertz, and he finally succeeded in it at 160 megahertz. So this was a confirmation for what Jansky had proposed, and just to give you a picture, that's Grothe-Reber's antenna that he had in his backyard. I'd be hard pressed to put that in my backyard without getting in trouble at home. And he actually tried to get a quote to build this, and it turned out it was too expensive, so he just built it all himself. It was quite a remarkable feat. So the next big development really was that spectral lines were predicted. So it was predicted that because the most abundant element in the universe is hydrogen, we should see this 21 centimeter line that results from the change in energy levels from the spin direction of the electron around the proton. And that was detected in 1951. That's the actual antenna that was used to detect it, with one of the two men who's I've forgotten who this is now, but he discovered or was one of the co-investigators to detect that line. And that was in 1951. So now suddenly we had the ultimate tool for mapping the universe, for detecting what is out there, and for figuring out by using Doppler shifts where it's moving and how it's, galaxies are rotating. And so suddenly we've opened up this enormous physics lab in the universe, and radio astronomy really hit the big time. So why radio astronomy? Well, there is this phenomenon of we have these windows. So the atmosphere, via various mechanisms, blocks out a lot of the radiation that comes into us. Obviously, we get visible light. There's a nice big window of a visible light. But then most of the rest is kind of obscured. But in the radio frequencies, from about the centimeter to the 10-meter wavelength, is a very nice open window. And we can actually, from Earth, we can observe very clearly what goes out in outer space. So this is a very handy area to do research on Earth, relatively cheaply. And we can look at various types of emissions. I'm not going to go into any of the details here, but we can look at thermal emission, we can look at non-thermal emission, which could be various forms, and we can look at spectral line emission. So there are both broadband aspects we can look at and narrowband aspects. That's all I want to say about this. And so people started investing in tapping into this enormous physics laboratory in the sky. And the Lovell telescope was really one of the first big ones to get built. It's a 76-meter diameter dish. It was fairly substantially upgraded after it was constructed, so it didn't look like this right at the beginning. But this was constructed out of spare parts from warships from the Second World War. And some of the mechanisms here are straight off the warships, and it's still in place today. That's in the UK. So that started really now getting into some serious science. That led to the realization that you want to have more sensitivity, and I'll get to sensitivity in a little bit. And so people started building bigger and bigger radio telescopes. So this is Effelsberg in Germany. That's a 100-meter diameter dish, and it's fully steerable. So it's a massive structure. That massive structure deforms under gravity, so as it rotates. And what they did to compensate for that is actually to design the structure to always deform into a parabola. And so the focus point would move depending on where you're pointing, but by moving the receiver, you could actually compensate for that. So you could still stay in focus. But you could appreciate that this gets kind of complex and therefore expensive. Next up was the Green Bank telescope. So this is in West Virginia in the United States. It's an offset Gregorian feed. You can't really see the details of that too much. Again, a fully steerable dish. It's 100 meters effective diameter, so it's about 100 by 110 meters. And in order to compensate for the gravitational loading, they made it out of panels. This picture isn't a real picture. The contrast is highly exaggerated, just so you could see the different panels. So there are 2,004 of these panels, and they need to be aligned to be able to measure up to sort of 100 gigahertz frequency ranges, so really tight tolerances. And in order to achieve that, they built actuators at the bottom, so every panel can be every corner can be individually moved up and down depending on where the telescope is pointing. So again, this starts to get very expensive, and it starts to get a little bit more complex. The next step up is the Arecibo telescope in Puerto Rico. This is 305 meters across, but this dish is not steerable at all. This is built into a natural depression in the earth, and the only way to steer this is actually to move this feed system up here, and it can steer, I think it's up to 45 degrees. And so this telescope can only track a source for about 2.5 hours as it comes across. So you get nice big collecting area, but you are limited in other ways. And as in many cases, the Chinese are taking this to the extreme. So they're building a similar system, but this is 500 meters across. It's a massive collecting area. And that's the FAST telescope. So a tiny little bit of science or maths, if you like. I've mentioned sensitivity. So sensitivity gives us the smallest signal that our telescope can detect in space. So obviously, as we look further and further back in space, the signals get fainter and fainter, and some of them have been traveling for 13 billion years, so you can't really blame them. So if we look at this sensitivity equation, I don't want to point out too many things, but there are a couple of things that are important. The one is the effective area. So our collecting area gives us more sensitivity. So we can go down to smaller signals. We can measure down to smaller signals if we have bigger collecting area. And then on the other side, we have things like the system temperature, so the amount of noise that our system contributes to it. And then also below, we have bandwidth, and we have basically the integration time, so we can observe for longer times. So that gives us this drive to bigger collecting area. Bigger collecting area directly, all else remaining constant, directly gives us better sensitivity. On the other hand, we have resolution. So from the optical field, you'll probably be familiar with this, that the resolution is proportional to the wavelength divided by the diameter of your dish. So if we have a single dish, then we're limited in the resolution by the size of that dish. And then there were some more interesting developments in radio astronomy. So back to the UK, in 1964, Martin Ryle and his co-investigators published the first results from using a technique called aperture synthesis. And they used the 1 mile telescope for this. And what this enabled them to do is to increase the resolution in the image by using the spacing between antennas. And so now, instead of that being the diameter of a single antenna, we can now take two smaller antennas and put them a large distance apart and get back the resolution into our images. And that brings us to the reason for the existence of a correlator. So just very briefly, if we have these two antennas and we have signals coming in from out of space, the example here is a quasar 3 billion light years away. I don't know exactly which one that might be. Then these signals would arrive at these different telescopes, obviously at slightly different times. And by just compensating for that delay, we can then correlate the two signals from these two antennas, and we can get back to producing images. There's some signal processing that needs to happen beyond that. So that now drives the whole of radio astronomy suddenly in a different direction. Instead of making bigger and bigger dishes, because the dish cost scales roughly with the diameter to the power 2.7, we can now make larger radio telescopes out of multiple smaller antennas. So this is the Very Large Array, or recently renamed the Jansky Very Large Array in New Mexico. And here we can now see that if we look at those baselines from the previous image, like that, we actually have multiple baselines here. So we have a baseline between every two antennas. We have a baseline from there to there. We also have a baseline from there to there. And so now we need to correlate all these baselines. And if you work out how many baselines you have, it turns out that the number of baselines scales with the number of antennas squared. You have to make up all the combinations. So it's two adjacent and all the others in that arm as well. And so you end up with a signal processing problem that scales as number of antennas squared, or n squared as we like to call it. That would obviously be a substantial problem. But this is where one revolution met another, if the slide will progress. And so here we get radio astronomy meets Moore's law. Moore's law basically is an observation, not a law, that stated that the cost of processing essentially halves roughly every 2 years, between 18 months and 2 years. So processing is getting dramatically cheaper. At the same time that complex structures and large structures have been getting more expensive, scaling roughly with diameter to the 2.7. So this is exactly what we needed to drive this explosion towards telescopes made up out of multiple smaller dishes. And to give you an idea, here's the picture. Okay, we lost the picture. There's a picture of resolution there. I can see it, but you can't. Which just gives you a comparison of the different baselines, so you can see the resolution in the image. And it really is like focusing a camera, so you get more resolution as you get the longer baselines. So that led to a variety of telescopes worldwide, and it ultimately, in the late 80s and early 90s, culminated in the world saying, well, how do we take the next step? And that was the start of the square kilometer array. So the next step up, they said, well, we need to take a step by 1 or 2 orders of magnitude in our measuring capability in order to drive the science beyond what they could do then. So that was a square kilometer of collecting area. Add up all the dishes, the areas of the dishes, and you end up with 1 square kilometer. And as part of a fairly long-standing strategy and policy of driving towards our geographical advantages in South Africa, the government decided that astronomy was one of these key areas where we had a geographical advantage, and they wanted to take advantage of that. So we started to invest more heavily in astronomy, and SALT is one of the results of that. And our involvement in the square kilometer array is another. And so when we started with this bid to host the SKA, we were in competition particularly with Australia. Australia had a fairly long and rich history in radio astronomy, and not taking anything away from the very good radio astronomers in South Africa who were doing very good work, ours was a lot lower profile than theirs. So we decided to build a radio telescope just to show the world that we could do it, and Cat7 is the result of that. So Cat7 is in the Karoo. It's 7 of these dishes. They're 12 meters across each, and it's made out of what was at the time a fairly novel structure. So it's a glass fiber dish with a steel backing structure. Cat7 was originally intended only as an engineering array. So it was for us to test our manufacturing techniques and to test our engineering processes. But right now it's taking science data, and it's actually the first couple of papers from it have been published already. And that's leading to the next step, which is Meerkat. So this is really a slideshow of Meerkat construction so far. But the Meerkat dish is another change in direction. So instead of being a center-fed single pixel feed, it's an offset Gregorian, and the offset Gregorian allows us to have a turret rotating in different feeds. So we can have different bandwidth feeds and different band feeds switched into focus. So this is an idea of what that structure looks like in construction. And if you put that on a truck, it looks a bit like that. And then you can transport it carefully. And if you plan everything very well, then by the time you get there, you also have a pedestal to mount it on. And if it's a large project with lots of political support, then you can afford to have a photographer around to take pictures like these. And then you take a crane and you lift that entire structure. So you can see that they've removed some of the panels in the center there in order to lift this dish up onto the pedestal and install it that way. And then finally replace the missing panels again. And then ends up, sorry, it's just another picture. So once the dish is up, then this whole arm here with the secondary reflector up there and the turret will be mounted there, can be installed as well. And finally, it looks something like that. So that's the first dish up from Meerkat. That's the only one we have so far, but we're working very hard on the rest of them. So taking a step back, this is just one of 64 dishes for Meerkat. What is the signal processing that needs to happen there? And again, I don't want to go into any detail. You probably can't see the detail. But basically, we get signals back from an antenna. That is processed, and in our case, our correlator is an FX correlator, which means we do channelization first. We break it up into frequency channels first, and then we do the correlation or the cross-multiplying of those channels. So those signals come in directly to a processing engine here, which performs that first part of the algorithm. And then we distribute that signal via a 10 or a 40 or a 100 gigabit Ethernet network to the second part of the processing, which is the X engine. So this part is per antenna based, and then it needs to cross over because then you need to get the baseline data. So now you need all the same frequency channels from all the different antennas in one place in order to do the correlations over here. So this part is per frequency channel based. So there's this big crossover. And the way we achieve that crossover, what we think elegantly, is by using an Ethernet switch, because Ethernet keeps getting cheaper and cheaper. So that's really the first part of the processing there. And if we look at the processing loads here, we saw some processing earlier on for the people who were in the Gaia talk as well. So just adding up all the processing, I've broken it down here. These are very rough numbers. We get to a total processing load of 170 teraops per second. So I call that teraops per second deliberately, because most of the processing here is based on not based on floating point numbers. We can use fixed point numbers, and sometimes we can even use numbers with resolution as low as 4 bits. The signals coming in from space is just noise, so we don't need all that much resolution to deal with it in the first instance. So at 170 teraops per second, if we wanted to build that with a traditional computer, then by the time I wrote this originally, which was end of last year, that would be number 149 on the top 500 supercomputer list. So this is a substantial amount of processing. Bear in mind, this is for Meerkat, which is much smaller than SKA, and it needs to be scaled up by probably several orders of magnitude for the full SKA still. So that technology on the top 500, particularly the computer it would have to replace, in 2010 that dissipated 510 kilowatts. That is a showstopper for us. We couldn't use that much power. It's just too expensive to get it there. Of course, processing advances very rapidly, so Blue Gene could do the same thing now at 82 kilowatts. We're still looking to process that slightly differently, and to reduce that figure by another factor of 4 or so. So a brief look at the other challenge. So processing is one thing, which could probably be done in commodity computers if you could afford the power bill. But at the other end, we also have a huge data rate coming into this telescope. So from every antenna, we have 40 gigabits per second streaming into the correlator. If you add that all up, that's 2.3 terabits per second. And bear in mind again, that's on Meerkat, 64 antennas versus the thousands of antennas that we're thinking of eventually for SKA. And even on the output side, the numbers are quite high. These numbers are much more civilized. They're gigabits per second, but they're still hundreds of gigabits per second. So this leads us to another challenge. We can't get that data into a standard computer. It might be able to process it, but we can't get it in and out. And so we have to build custom hardware. And this is one of the pieces. This is called the digitizer. So this box sits on the antenna. It gets the analog signals in, samples it, and then packages it onto Ethernet packets and sends it back to the correlator. So these are the two RF connectors, and there are only 3 copper connectors to this. It's the 2 polarizations of the radio frequency signal, and on the other side there's a power connector. And then this is a fiber optic connector, and that's where the 40 gigabit Ethernet signals go out. And from there they go out to a subsystem that looks something like this, hopefully a lot neater. This is our lab, it's a mess. Apologies for that, but it gives you an idea. And these boards are our processing boards, so they a little bit like PCs for radio astronomy, but they're not using generic processors. They're using something that we call an FPGA. It's an acronym for Field Programmable Gate Array. And a Field Programmable Gate Array is really just a sea of gates that you can configure in any way you like. And because we can configure them in any way we like, we can process the exact bit widths that we need at any stage of the processing, helping us to make this thing more power efficient than it would with standard computers. And if we take a closer look at one of those, they're actually called roaches. So Roach is a reconfigurable open architecture computing hardware. I'll have a quiz on the acronyms at the end. And this is based on an idea that started at the University of California, Berkeley, to try to reduce the cost of developing radio astronomy instruments. And this idea was based on multiple institutions collaborating on the development of the hardware platforms. So what we're saying is we want a few hardware platforms. We don't want hundreds of different custom hardware platforms. And we want to all collaborate on the same platform so that we can share our resources and therefore reduce the development cost. If you reduce the development cost, then you can afford to track Moore's law more aggressively. So every time a new chip becomes available, we get a new board and our instruments become better. So I'm going to skip straight over a whole bunch of other stuff. One of the things I'm going to skip over is this is the beginnings of it. It's a tape drive system that will implement a 10 petabyte archive. So with our 2.5 terabits per second data coming in, we just can't afford to store all of that. It's too expensive. So we do various data reduction processes along the way, and also quality assurance processes to get rid of any radio frequency interference that might contaminate the signals. And then eventually we reduce the data rate down to a rate where 10 petabytes is enough to store some useful information. It still doesn't store it infinitely, but at least we can hang on to it until we've decided that it's good. I'm also skipping over the later signal processing aspects, so these inverse two-dimensional Fourier transforms that produce what sounds a bit like pornography but isn't, the dirty images. And then the final one is the radio interferometer measurement equation over here, which is how we try to go from these dirty images to cleaner images to try to get the actual picture that's out there. But you're more than welcome to ask me about this or to read up more about this if you feel like it. So all of this is going into the Karoo. This is our Karoo array processor building. It's actually in the corner there. What you can see on this picture is this picture is taken from a berm which we created on this side to shield all of this equipment from where the antennas are. So, radio frequency interference is our enemy number one, just similar to light interference for optical astronomy. And so this location was chosen to be in a radio quiet zone where the average density of people is about 4 people per square kilometer or below that, and you get more sheep. And therefore we have fewer telephones, computers, radios, anything else that could cause interference. But of course, having chosen this pristine radio quiet location, it wouldn't help us anything if our own systems interfered. So a lot of effort was put into making sure that we keep this environment radio frequency quiet. Some of the big structures you can see in the back here, that's the dish shed. So the dishes are assembled here, and you could actually do 3 in kind of a production line at one time. And at the back there is a pedestal assembly shed, so the pedestals, all the components could be shipped into site and then assembled there. So if we're going to put down a supercomputer there, then clearly we're going to cause interference. And the way we mitigate that is by building the entire supercomputer in a shielded room. So it's a Faraday cage, and you can see that the walls are all metallic, and they're all connected, and they have gaskets in the seams so that no radio frequencies can escape from here. And there's a double door that you have to enter, both with shielding included. So all of the computing equipment that we install will be installed in racks, as you can see, like over there, inside the shielded enclosure. And all of the signals coming into the shielded enclosure would be on fiber optic. In addition, you can see here, this is fairly standard for data centers. It's underfloor cooling, so the cooling air escapes out of these cold aisles. So this would eventually be a cold aisle, and these are power connectors. And then the hot air is sucked through the ceiling. And of course, all of that needs to be powered. And this is one of the, from an engineering perspective, for me, one of the marvels of this thing. these are the rotary UPSs. So we get power in from Eskom, but we don't actually use that power directly. That power drives a motor, which drives a flywheel, which drives a generator, and we use the power from that generator. If the incoming power fails, these units will use the energy in the flywheel to start up a diesel motor that will give us uninterruptible power. And this is kind of, I think it's in the order of 5 MVA capacity eventually. We're below that at the moment, but for SKA phase 1 we'll go up to 5 MVA. And these are massive 16-cylinder diesel motors, and they're up to full load in less than a second, which is, to me, was quite impressive. And what's even more impressive, of course, if you have that much mass rotating, then things could get unstable pretty quickly. So they're so well balanced that if you balance a coin on its side, on the side of this machine here, and you start up the diesel motor, the coin still stays standing upright. There's some famous pictures of that, actually. Okay, so that moves us on to the square kilometer array. Now, Meerkat is being built at the moment, and by the end of 2016, we will have engineering completion, which means we go into a commissioning phase, and by sometime in 2017, we'll start taking science data. And beyond that lies the square kilometer array, and the square kilometer array really is going to build on Meerkat. So Meerkat will actually be incorporated into the square kilometer array component that's in South Africa. The square kilometer array will consist of many different elements. I'm not sure how clear you can see this one here. That's the low frequency aperture array, and those are really just dipole antennas scattered over the ground, and they don't actually look like much. The second part is this. This is the sort of dense aperture array. It goes slightly up in frequency, and this is just the radome that covers it, and you could see anything up to say 11,000 elements underneath one of these. And then the third element is this dish element. And the dish element is the one that's coming to South Africa in the first instance, and that's the one that Meerkat will be incorporated into. So this is an artist rendition of what that might look like by, say, the mid-2020s, when the core of SKA is completed. So it'd be a really impressive sight. And you can see this distribution of the antennas, very dense in the core, and then getting more and more sparse as you go out further to the longer baselines. So there's this balance of collecting area and the baselines, which give you the resolution. And the best balance between the two with fixed antennas is a sort of a Gaussian distribution where the core is dense and then it gets less and less dense to the outside. So this would be a picture of what the SKA, the final SKA, is estimated to look like. And that might be thousands, 2,000-3,000 antennas distributed out over distances up to 3,000 kilometers. So in South Africa, those remote outlying stations, well, in Africa, those outlying stations are going to be not even in our neighboring countries. They're going to be in countries as far as Ghana and Mauritius. So it's a huge undertaking all the time, bearing in mind that from every one of those antennas, you have to bring this massive data stream back to be correlated with all the other antennas. A quick look at the aperture array low from a little bit closer, and again, it's difficult to see. These are really log periodic antennas, and they just distributed out of the ground, and you can actually see the mess of cables interconnecting them all. This is going to Australia. And then this is the aperture array, the mid version of the aperture array. So again, I mentioned looking at order of 11,000 elements in each one of these circles. You can see the number of circles that they're proposing here. So this is a huge signal processing problem. In fact, so big that they've decided that for SKA phase 1, this isn't viable. So this will only happen in SKA phase 2. And when it does, it will also come to South Africa. Okay, so I hope I've given you a little bit of an overview of the radio astronomy road to South Africa and a little bit of an idea of the activities of radio astronomy in South Africa. And I, for one, am very grateful that our government is investing in this. I think a lot of us in the project come from military backgrounds, maybe, and being able to work on something that you can tell people about is really a privilege that you only realize when you can do it. Thank you very much.
Thank you. We've got time for some questions. Are there any questions? Yes.
Thank you for the presentation. Very interesting. I still have this picture in my mind of you guys all sitting around in the Karoo eating lamb chops, but I have a
That's accurate
question, and I don't know if you can give us some idea of the type of signals you can resolve now compared with that 1950 Lowell telescope. You know, because obviously radio technology has improved tremendously. And then also, were they doing all their processing in analog realms back then?
Yeah, so it started off like that. And in fact, even the first correlators were analog correlators. So it was a gradual process to go from analog processing to digital. So one nice story is in 1967, Jocelyn Bell discovered the first pulsar. And this discovery was made on a paper tape. So it was basically a chart recorder. And she looked at these rolls and rolls of paper, and she had to do her measurements on that paper. So it was literally a pen and marking out things and measuring the difference, time arrival differences between the pulses, and finally figuring out that. So that whole or move towards digital is relatively recent. So in terms of resolving power, the best way would be to use some images, but I don't have any handy. But yes, I mean the kind of processing we do today is absolutely, it's advanced in leaps and bounds. So it's very difficult to compare what they could do then to now. What is interesting though is that the Lowell telescope is still in use. So that collecting area has tremendous value in its own right. So by just replacing the backends and the feeds, if you can make broader band feeds, for instance, you can still really use that. And that telescope had a very funny story that comes to mind. Is one night they were operating and there was only a lone operator there, and a sudden gust of wind pushed it towards one side, and it was within millimeters of falling off its bearings and collapsing. And the operator was quite a quick-thinking guy, so what he did is he rotated the telescope in the opposite direction, and he was really lucky. There was another gust of wind and it blew it back. So it went back onto its proper position. But yeah, so some things change, but collecting area has a value that stays around.
Another question? Got time for one more? Yes. Up there.
Okay. All this data, who's going to process it? And who's going to shout wow when they see something?
So one of the science projects is on SKA particularly is the search for life outside of Earth. And I'm not sure what the protocol is, but I mean, if someone detected intelligent life somewhere, that would really be a big deal. And I think in the SKA's case, the governments of the member countries would probably be notified first. The processing happens in various stages, so there's no point in everybody building a supercomputer to process all the data. So there'd be a certain level of processing that happens centrally, and there'd be a supercomputer built to do that. And then you get your data products from that, and those might be images or image cubes or that kind of thing. And you could process that further, and there'll be regional science centers to support that kind of thing. So with probably more modest supercomputers to process that. But the initial products, the whole quality assurance of that, all of that needs to happen centrally. So it's the domain of the SKA organization.
Okay, Melvin, you had a question?
Yes. How steerable are these dishes?
They can go down to 15 degrees above the horizon, no other limits.
They can rotate.
They can rotate, yeah. So you obviously have cable wraps. Sometimes you'd have to go back, but you can rotate it. Yeah.
But full visibility.
Full visibility, yeah. So most of the science projects, the surveys particularly, would be integrating on the same field for maybe 5,000 hours. So every day you would wait for it to rise, track it through the sky. The next day you go back and do the same thing.
Charlie, you had one?
Yeah. The supercomputers that are going to be developed in the future
Yes,
to process SKA.
Yes, they have to be.
But now, are you able to process the signals now with existing supercomputers in the various countries like Russia and America and stuff like that?
So neither Russia nor America are member countries of the SKA. There are supercomputers being planned and built and have been built. So Australia have already built their supercomputer facility to process their equivalent of Meerkat. Their precursor is called ASCAP.
So are we building ours now?
And we are busy designing ours. But Meerkat will only be finished in 2016. So with supercomputers, you want to build them as late as you possibly can.
Why is that?
Because the technology just develops so quickly. So the later you buy the hardware, the more hardware you get for your money. So we're not going to build it and wait for the telescope to be ready. We'll build it at the last minute.
But obviously, with the Australians building theirs already, okay, and they haven't even built their Meerkat on their side.
So their system is a little bit ahead of our Meerkat system. We built Cat 7 first, and they started with ASCAP directly. So they have 6 antennas up out of the 36 that ASCAP will be. They've gone for a much more risky technical approach. They're using phased array feeds. And I think that's part of the reason why there's only 6 of the 36 up, is because that's proven to be quite difficult to fix. So it's a slightly different approach. So with 6 antennas only, or 36 antennas only, the scope of their processing problem is less.
So will we piggyback on their research that they've done already for their supercomputer?
Yeah,
to make
and
ours twice as good or something?
And vice versa, yeah. So the research supports both ways, and throughout all the other member countries too.
Okay, last quick question, then we must close.
The impact, what is your opinion on the impact of potential fracking in the Karoo and the SKA? Because it's pretty severe.
So I have a personal view and we have an organizational view. The organizational view is that we have legislation in place to protect the radio environment. So radio telescopes are going to be less sensitive to some of the seismic effects of fracking than would be optical telescopes. So we're not too concerned about that. It probably wouldn't bother us. What we are concerned with is any kind of development will bring with it two-way radios, communication systems, and other noises. We have legislation in place. We can shut them down if we have to, and we will do. But at this stage, we're working with anyone who's going into that area and trying to assist them not to interfere in the first place. Personally, I think fracking is a really bad idea.